This is the third lesson in the Year 8 Binary Bits and Bobs unit, and what we will take a look at today is how computers represent text in binary. So here's a starter slide. We've got the little man saying that he knows binary, that this binary number has the denary value of 65, and it's absolutely right. The binary value 10000001 represents 65 because it's one lot of 64 and one lot of 1. Add 64 and 1 together and you get 65. However, the Android is saying, actually no, today this number represents the letter A. And the Android is correct as well, because depending on the job that the computer's doing, 65 could indeed mean the capital letter A. So over the next few slides we'll hopefully have an understanding or learn about why that is the case. So what I want us to take a look at is a quick reminder of how the binary number system works. We're going to hopefully understand why it is that computers can only work in binary, and understand that in a computer system characters, whether they're letters or symbols on a keyboard, that they are all represented with their own unique binary numbers. So as we've seen before, computers, they only work in binary, and the reason for that is because computers are ultimately just made up of switches, and those switches can be in one of two states. So therefore the computers, the switches, can only hold one of two possible values at any given time, hence the binary number system. Now all data, whether it's numbers, text, sound or images, they all have to be converted into binary for a computer to be able to process it. So in a computer system, each character on a keyboard, whether it's a letter or a symbol, or whether it's even a space bar, because a space is a character, they each have their own unique binary number. So the binary number 10000001 can indeed mean the number 65 in decimal, or it could mean the letter A, depending on the job that the computer is doing at that time. Now here we've got the ASCII table. Now ASCII stands for American Standard Code for Information Interchange. And ultimately what it is a universally accepted set of binary numbers that each represent a different character that you find on a keyboard. So in green you can see that we have got different characters. We've got the character, the capital letter M, for example. That is represented by the decimal value of 77. So that letter is given a number, it's given its unique number of 77. Lowercase m has got the number 109. So uppercase and a lowercase m, they're two different characters. Okay, they've each got their own unique number to represent it. Ignore the hexadecimal numbers for now, okay, because we don't need to worry about the hexadecimal number system, but just concentrate on the idea that we've got characters and each of those has got a unique number assigned to it. Now as we know, computers don't work in denary, they don't work in decimal, they work in binary. So in terms of a computer, this table's obviously for us as human beings, but for a computer each character will have that number representing it in binary. So if we have a look at trying to do a little bit of a challenge with these. So what is my name? Now let's have a look. We've got here the binary value 10100011. Now in order to work out what letter is represented by this binary number, we need to convert it into decimal so that we know what we're working with. So let's have a look at doing that. So we've got one lot of 64, we've got a 16, and we've got a 2, and we've got a 1. Well, if we add 64 and 16 together, we get 80. If we then add 2 and 1 onto that, we get 83. So this binary number is 83 in decimal, and that, on our table, 83 represents the capital letter S. So that first binary value is representing an S. So you can see that there. If we then have a look at the next one, 100101, that value is 73, and if we look at up what 73 is on the table, you'll see that 73 is the letter I. And finally, the last binary value there is 82 in decimal, which represents capital R. So my name, of course, is Sir. Let's have a look at another one. And it might be worth you pausing the video once I've gone on to the next slide and seeing if you can work it out before I start explaining what that name is that it's trying to hide. So pause it now if you like. Okay, so whether you've had a go yourself or not, let's have a little talk through or a walk through each of these binary values. So 64, 16 and 2, that is the number 82 in decimal. If we look up 82 on our table, you'll see that that is the letter R. So 82 is the letter R. The next binary number represents 73, and 73 represents the letter I in the ASCII table. Then we have 78, which represents an N. Then we have 71, representing a G, and finally 79, which represents an O. So my name in this case is Ringo. Now that's a very strange name, but that was the name of the drummer in the band The Beatles back in the 60s. So hopefully now you've got some understanding of the idea that if a computer is to represent text, each of the characters that you would have in the text would have its own binary value.